everybody? Happy Tuesday. Thank you. So I know you all experienced that brief shining moment where your homework is done and you're like all caught up. Sorry to tell you that shining moment is over. Your next homework is now available. You can put it off for a while though if you want, because it's not due until the 23rd. It's a Wednesday, because I wanted to make sure that we had enough classes before to give you at least a full week to work on it. It's a longer one. You can do everything through section 4 right now, and 5 and 6, hopefully after today or next week at the latest. So now I have the brief shining moment where I'm all caught up with homeworks and I don't have to make them, so we just trade off. I'm also reasonably caught up on your lecture materials because example B and lecture B are going to take us a little while to go through. I looked over the scores. Looks like most things went pretty well with the homework. If you have questions about why you got something wrong, or if you think there's an error in my coding for what should be correct, please don't hesitate to let me know. I'm happy to answer those questions. If you got something wrong, your answer will be red, and then what it should have been will be in green. So, all right. You'll have a quiz to do this week while I am gone, and we'll talk about that next Tuesday, so no class on Thursday. A little bit of a fall break for you. I will be in Baltimore at a conference. Woo! And I'm not bringing my son, so woo! The last time we went to this conference, we brought him. He was 2. So he's staying with Granny and Papa this week. Which thank you, Mom and Dad. I owe you. So, something like a vacation. It's amazing what passes for a vacation in your 40s, isn't it? Yeah. So thanks for coming back. We can do some reviewing of level 1 predictors. We started talking about between, within, and contextual effects. So the basic premise, level 1 predictors, is that any predictor that is measured at level 1 is likely to contain level 2 variation as well. So to the extent that it has an intraclass correlation greater than 0, you got to worry about it having level 2 variation and thus having its own level 2 effect. So far we have talked about 2 ways of specifying level 1 predictors in the model to be able to delineate their level 2 from their level 1 effects. This first one is the one that we did in our example. It's called group mean centering. This is the one that I prefer for its ease of use and interpretation. So this is where we literally carve up the level 1 predictor into 2 new variables that each contain only 1 level of variation. So in this, I'm starting on slide 32 in lecture 3A. I have within group X. That's my name for this because it's the original level 1 X minus the level 2 group mean. So I'm subtracting a variable, not a constant. That's a very, very big deal. Variable, not constant. So that means that within group X has only level 1 variation. Therefore, its fixed effect in the model, gamma 1O, can only be the level 1 within group effect. At level 2 then, we take that group's mean, center it at a constant so that 0 is meaningful, and we put that into the level 2 equation for beta 0. So because this level 2 predictor only has level 2 variance, its effect can only be the level 2 between group effect. So each predictor has its own job to do at each level of the model. To the extent that the within group effect is significant, that having more of X than other people in your group matters, the level 1E residual variance should go down. To the extent that being from a group that has more X on average than other groups matters, the level 2 random intercept variance should go down. Nice and tidy, right? Okay, questions on any of that? So this is the specification that I'm asking you to do in homework 3, because this is the one that is easiest to start with. So here's some pictures that show what that looks like. We looked at these pictures last time. Now the other way of doing it, using the level 1 variable centered at a constant instead of a variable. So reviewing the way that the 2 level 1 variables are made, group mean centering here, the within group column, we have taken out all of the group level information, and so what's left is group relative. Whereas if we just center at a constant, So 5 in this example is the mean of the variable. It could be any number or not, including 0. But if we don't center at a variable, if we center at a constant, the level 1 predictor still contains level 2 variation in addition to its level 1 variation. So its effect in the model changes as a function of whether or not you also enter the level 2 predictor to control for that variation. So this is the other way of doing it. In this case, the level 1 predictor, this is where we ended up with last time, the level 1 predictor still has level 2 between group variation in it. After we control for level 2 between group variation by introducing the group mean in the level 2 model, the level 1 predictor has a unique effect that becomes the within effect, the same as in the other model. So what group mean centering accomplished by literally carving up the variables, this is accomplishing through statistical partialing. There, nailed it that time, right? Yeah. However, group mean has to compete against the level 2 variation in the level 1 predictor. So its effect at level 2 is not the between group effect, it's the contextual effect. It's the unique between group effect after controlling for the level 1 predictor. So we looked at this picture. We'll put this back up again. So this picture shows the 3 different effects that we would be interested in for a level 1 predictor. So the x-axis is the level 1 predictor, the y-axis is the level 1 outcome. The lines are for separate schools who vary in their means on the level 1 predictor. The slope of each of those lines is 0.5. That slope is the within school effect. For every unit more reading you have than others in your school, your math in this picture goes up by 0.5. Either model will give you that as your level 1 effect once you've included the level 2 group mean. What happens at level 2 depends on which level 1 variable is paired with it. The effect of the group mean changes depending on which level 2 variable, level 1 variable is paired with. The between groups effect is the slope through the school means of this yellow line here. That's 2. For every unit higher school mean x, school mean math goes up by 2. This yellow line is not controlling for the individual student reading values. To do that, we need to go to the black vertical line instead, which is anchored on 5 in this case, although these lines are parallel, so it would be the same at any point. But the idea is that after controlling for reading, so conditional on the same value of the level 1 predictor, then for every additional unit school mean reading, school mean math goes up by 1.5. So part of the level 2 between group effect is due to the individuals. After you subtract those individuals, then you get the contextual effect for what's left. So level 2 contextual is the effect of the group after controlling for the individual. Level 2 between is the effect of the group not controlling for the individual. It can be tricky to figure out which of these your model is giving you. If your level 1 predictor only has a fixed effect, which up to this point that has been true for us, the difference between these models is trivial. One is a linear combination of the other. So to show you this, let me revisit example 3a real quick. Here's one of the models in which we had a level 1 predictor for verbal IQ, so within school and school mean, so we're using group mean centering, as well as the same for performance IQ. And one of the linear combinations that I asked for right here is the contextual effect. If you're using group mean centering, the level 2 predictor gives you the between effect. The level 1 predictor gives you within effect. The difference between those two is the contextual effect. So by multiplying the between slope by 1 and multiplying the within slope by -1, essentially what you're doing is subtracting the within effect from the between effect. That's contextual. So this is what you would have gotten had we done grand mean centering instead of group mean centering at level 1. So in your homework, you'll get a chance to practice doing these as well. So giving a couple more examples of this, socioeconomic status as a continuous predictor in this example. I have a real-life one using a categorical version of it. So for instance, if I'm worried about the effect of SES on student achievement and students are nested in schools, if I set up a model with group mean-centered student SES, so the level 1 predictor is the relative difference in SES relative to your school. Level 1 coefficient is the within group effect, the effect of having more SES than other kids in your school. The level 2 effect is the between effect. It's the effect of going to a school with higher SES kids, not controlling for your own. In clustered data, it often makes more sense in terms of the research questions to do it the other way, grand mean centering. When done properly, when the school's mean is also included, meaning done properly, the level 1 effect is still the within group effect. It's the effect of being a relatively rich kid, richer than everyone else in your school. And the level 2 effect is the contextual effect. It's the extra effect of going to a rich school after controlling for your own SES. So what is the effect of the school environment above and beyond individual characteristics? A lot of educational research questions are phrased that way. The same happens in like IO psychology, organizational research. What is the influence of the company's climate? Those kinds of questions, they lend themselves to this approach. Here is a picture that there's a recent article that was just published that I added to your reading list earlier in the semester, talking about sort of what happens when you have different types of contextual effects, because it can be challenging in certain models to figure out whether you have a between effect at level 2 or a contextual effect. So the first picture is what several of you asked about at the end of last class. I think, Changpeng, you were asking me this question. What would it look like if you had no contextual effect? It would look like the top picture. So in this case, this picture was generated by having a within slope, so the slope of these individual lines of 1, a between slope through the means of 1.2, and the difference of those slopes is the contextual effect, is the vertical difference at the same point on level 1x of 0.2. So the way I would say this is that the between effect of 1.2 is 0.2 more positive or larger than the within effect of 1. And for such a small contextual effect, it may not be statistically significant, meaning that after you control for where you are on level 1x, the school that you go to doesn't matter. There's no extra bonus or detriment of going to a school filled with high kids or low kids. So this is a situation in which fitting 1 fixed effect instead of 2 could be reasonably okay. I still wouldn't recommend it though, because those effects can change after you add other predictors to the model or interaction terms. Now the bottom is a trickier situation. This is where the within effect is 1, so the slope of the individual lines is 1. The between effect is 0. So that's the dotted line through the means here. So going to a high school doesn't help you. Being a high person relative to the rest of your school does help you. However, with the between effect of 0 and a within effect of 1, that gives a contextual effect of -1. So that means that after you control for where you are, going to a higher school is associated with lower outcomes. So it matters then, if you're asking, what is the school effect? The between effect is the school effect, 0. The contextual effect is the school effect after controlling for the individual is -1. So in this instance, at the same level of students, say SES, relatively high students from low SES schools do better than relatively low students from high SES schools. That's what that means. So it's imperative to know which you get from these models. So let's put this together. So if I do group mean centering, and so I have a, let's call this within group X equals X minus the group mean for my level 1 predictor. And I have my level 2 predictor is the group mean minus some constant. Versus grand mean centering, where my level 1 predictor is just X minus some constant, and level 2 is the group's mean minus some constant. Okay. So, different variables at level 1, same variable at level 2. Now, what do we get in each combination? If I put in, let's see here, make a little thing here. If I put in level 1 only, level 2 only, or both, what do I get? Let's do group mean centering first. If I enter that level 1 predictor for within group X, what do I get? You have 4 choices: within, smushed, between, or contextual. These are the 2 possible predictors. What if I put in the level 1 predictor by itself? I get level 1. So that is within, smushed, between, or contextual. This one is within because this variable only has level 1 within variance. It can only have a level 1 within effect. What if I put the level 2 predictor in all by itself? Yep, within, between, contextual, or smushed are your choices. This one is between. This group mean only has between variance. It can only have a between effect. What if I put them both in at the same time? Does anything change? Nope. This is why I like this way. It's pretty hard to screw this up. In these models, for the term that's not included, what are we saying about its slope by not including it? It's 0. Same as any predictor that's not in the model, right? So I'll put that in. Now the fun part. Same question. Now using the grand mean centered version of the level 1 predictor. If I put it in by itself, your choices are within, smushed, between, or contextual. This one is smushed. How about the level 2 by itself? Between, same as above. Now about when they go together. This one is within because the level 1 predictor has been controlled for the level 2 variance, so it's been fixed. And that means this one is what? Contextual. There you go. So what smushed means is that this one that we're leaving out is implicitly the same. By leaving it out, you're saying there is no contextual effect, meaning that the within and the between are the same, and we only need one. This one, leaving it out, 0. So when I say that grand mean centering is easier to screw up, this is why. Because the effects change depending on what they're paired with, and they change in a way that is unpredictable. What's crazy about this is that in the column E, where they're both in the model, what goes in at level 1 is a different variable, but it ends up having the same within effect. What goes in at level 2 is the same variable, but it ends up having a different effect. So the two ways to screw up level 1 predictors: don't control for the level 2 part, that's one way, and the other is to mistake what you have at level 2 in each model, between versus contextual. Now that being said, there are certain circumstances in which grand mean centering this way, even though it's harder to get right, not impossible, but harder, this way would be preferred. So when would you want to set yourself up to do it this way? I can think of 3 situations. First, when what you actually want are contextual effects. Then the level 2 effects in the model are the extra effect of the group after controlling for the individual. If that's what you want to know, great, Godspeed. The other situation is when the level 1 predictor group mean centering would not make sense, such as when it is categorical. So if I have a binary level 1 predictor in which the only possible values are 0 and 1, group mean centering would create impossible values for it. The other situation is when the cluster mean is not a reliable measure of the group level construct. So in the slides where we're looking at, say, student SES, right? I can get a school level indicator of SES one of 2 ways. I can go to the superintendent and get some sort of archival data, right? Like proportion of kids who get free lunch, or the average income for the parents, or what have you, right? Like that can be a source of data that you collect and you can feel reasonably good about it because the school hopefully would have included all of the students in making that number. But if you don't have that and you're stuck with only the sample that you have, then the alternative is to compute the group's mean out of the sample that you have. Then you really gotta believe that the level 1 sample is representative of that group. So in the example that I'm going to show you, I have free and reduced lunch status. I have a whole bunch of schools and I kicked some out that had less than 30 people because I made that decision arbitrarily, but I was afraid of characterizing a whole school with only a handful of individuals without knowing anything else. So if you're in a situation where the information that characterizes your level 2 variable is coming from a different place than the information that characterizes your level 1 variable, even though they're kind of the same idea, grand mean centering would make more sense. And then it's not a strict contextual effect in the mathematical definition because the variables are not necessarily on the same scale, but it's the same idea. What's the effect of the group after controlling for the individual, just with a different variable? Okay. How are we doing? So last thing, that what happens in these models in terms of variance explained. So let's go over this case right here, because this might be more effective than the PowerPoints, but all this information is there. Let's start with this one. If I have a level 1 effect only, and I'm using group mean centering to create the level 1 predictor, and the within effect is significant, what should happen to my model variances? Level 1 residual variance and level 2 random intercept variance. Which of those two should be explained? Reduced. Level 1, yep. So should account for E variance, say that. Make these a little bit bigger. Hey, I didn't want whatever the hell that is. E, stop it. There. How about if I put the level 2 predictor in all by itself? which of the two variances should it reduce? Level 2 intercept, U0. So in this situation, when I've explained level 2 random intercept variance by including a level 2 predictor, and I don't have a level 1 predictor, what should happen to the level 1 residual variance? Should it change? Stay the same. Three choices: up, down, same. What happens to the level 1 residual variance in this situation where I have not included a level 1 predictor? Same. Yeah, we saw this in the example 3a. We added a bunch of school level variables. Level 1 stayed about where it should be. It might wiggle a little bit because in unbalanced data, like it's still trying to find these things, but it should not change by any important amount. So if you put them both at the same time, then you would see E variance goes down because of level 1. Stop that. U0 variance goes down because of level 2. And everything seems fine. So in your homework, I will ask you what is the specific effect size for different types of predictors. This is the idea. If I put them in the model at the same time, I won't get to see each of them change, but I know that that's why it has to be. Because the level 1 variable only has level 1 variance, it can only explain E. Because the level 2 variable only has level 2 variance, it can only explain U0. Has to be that way. Now, what do you think is going to happen in this cell? So I've explained the residual variance by entering a level 1 predictor. What happens to level 2 random intercept variance? Up, down, or same? There's your clue. Tricky. It's tricky to run unmodel, That's right, all the time. It's tricky. No? Thank you. You would think it'd stay the same, right? And it should, but it doesn't. The correct answer is that it's going to go up. There, U0, up. What? Here's why. So this is slide 49. The random intercept variance you get at level 2 is not the between group variance that's observed in the data. It has been corrected, adjusted for how much of it thinks is due to within group fluctuation. It approximates expected within group fluctuation that creates between group differences by this thing right here, the residual variance at level 1 divided by the level 1 sample size. So the observed between group variance is a function of what is truly there plus noise. So it tries to give you what is truly there by taking what is observed in the data and subtracting off the noise. So when E variance goes down and this one stays the same, this goes up. For example, let's say we start with an empty model where the level 2 variance that is the observed variance is 4.65. The level 1 E variance is 7.06, and there's 4 people per group. So it's going to say, all right, well, the observed variance is 4.65, but some of that's noise, so we'll take my 4.65, subtract the correction factor, residual variance over level 1 sample size, and what will show up on my output is actually 2.88. as my true between group variance. Let's say I add a fixed level 1 slope, and it was a big effect. It reduced my level 1 residual variance from 7 all the way down to 2 something. So about 70% of my residual variance is explained. Well, the observed between group variance hasn't changed. We haven't explained any of it because this is purely a level 1 effect. Observed between group variance is 4.65, but what has changed is the size of the correction factor that is subtracted from it. It's 2 instead of 7. So now we end up with 4.1 as our between group variance that's true, which is an increase from what it was before. So that is to say, this is going to happen. It's not a sign that you've done something wrong. It is a consequence of the estimation process. This is also the reason that if you start out with 0 for your between group variance, like an intraclass correlation of 0, and you think, hey, I have no dependency, I can go back to regression. It's going to move up off of 0 the second you explain variance at level 1. So yeah, so what ends up happening then is that I would talk about the effect of entering the within effect on the residual variance. I probably would not talk about this. Once I add the complementary part of the variable, this will come back down, and so you can do them both at the same time. So grand mean centering, let's do the middle column first because this is the same situation. If I enter a between effect by itself here, it explains random intercept variance. E same. There we go. The E variance should stay the same. Now what happens in this case? If I enter the smooshed effect, what's going to happen? Let's say that it's significant. It explains something. What's going to happen to level 1 E variance? It'll go down. It will go down. E is explained. Nope. Stop that. What will happen to the level 2 variance? It could go up, it could go down. It depends on how bad the smooshed effect is. If the smooshed effect does a pretty good job of capturing within and between, meaning they're not that different, then the U0 variance would go down. If the effects were in different directions, the U0 variance would go up. So if I fit this model first, and then I fix it by adding the level 2 group mean, E will stay the same. You're killing me. But by adding the contextual effect, it will pick up the rest of U0 that it should have had in the first place. There. Do you want to see this in action? Put some numbers on it, will that help? Okay, I think it might help. Example 3b. We can do the first couple models on this. So these are real data. They're a math test given at the end of 10th grade in a Midwestern rectangular state. So you'll have to figure out which one. 13,802 students are included in this analysis from 94 schools, somewhere between 31 and 515 students in each school. So we're going to predict student math from a binary level 1 predictor for whether or not the kids get free and reduced lunch, where 0 means they do not, they pay for lunch, and 1 means they get some sort of lunch discount. Free and reduced lunch status is a commonly used indicator of socioeconomic status. It's not a great one. There's a whole literature on that, but I am agnostic as to the theory here. I'm just showing you some numbers, okay? So this is an instance in which, because I have a binary level 1 predictor, group mean centering doesn't make as much sense as grand mean centering. Also, in the context of asking about the school environment above the individual, both of those things would lend me to use grand mean centering. And because my variable already has 0 as a meaningful value, I don't have to do anything to it. It goes in the model as is. So in your example or homework 3, I'm asking you to compute school means of level 1 variables as predictors. Here's how to do that. So in SAS, it's proc means by school, where you list the variables, you save the school means to a new data set, and then you use the mean function, and you can rename them. So in my vernacular here, SM means school mean. So I did that for the free and reduced lunch predictor as well as the math outcome, just to get some descriptive statistics. I then merged them back into the data set. School free and reduced lunch is the proportion of students in a school that get free lunch. It ranges from 0 to 1. The mean for the variable, which we'll see in a moment, was around 30%, so I centered at 0.3. I arbitrarily selected schools with only 30 or more people. I wouldn't recommend doing this in real life, but just to make this example, I decided to do that because I didn't have a school level free and reduced lunch variable that was more than just the aggregate of the individuals. And then I'm asking for some descriptives. The same thing in Stata is actually a little easier. If you haven't seen this before, there's a special egen that you can use to get school level. So it's the egen, the new variable, equals the mean of the old variable, and then by. It knows you're trying to do that across rows, and it appends that new variable directly into your data set. So, all right. Questions on the setup? Okay. Well, here's some descriptives. So N per school. So these are school level descriptives, and I'm using Stata output here, since a lot of you are intending to use that program for this part. School mean free and reduced lunch. Now, because this is a binary level 1 predictor, I'm not going to generate an intraclass correlation for it, because these models assume normal level 1 residuals. We need a different kind of multi-level model to get an ICC for a binary variable, and we haven't talked about that yet. But this is really all I need to know. Some of the schools vary from each other in the proportion of students who get free lunch. The minimum is 0. The maximum is 80%. That's all I need to know. Yes, there is school level variation in this level 1 student free lunch variable. And it looks to be pretty significant. There is also school level variation in my math outcome. The school mean in math is somewhere between about 30 and 60. On this scale, I think the highest at the individual level is 83. So this idea of mean level variance is what I'm going to use in intraclass correlation to quantify more exactly. And then here are the descriptives at the student level. Math scores range from 0 to 83, and about 31% of the students get free lunch in the sample. So first thing, empty model for math. Figure out how much variation we have of each kind and what kind of design effect we're looking at. I am bucking the system in terms of my notation. No more IJ or PG. I'm going PS, pupil within a school. Because why not have subscripts that make sense, right? You don't see that very often, but it really helps when you're reading unfamiliar notation to have something that you can easily map onto the variables and the levels of analysis. So I'm doing it PS, like, hey, PS, you don't have to use IJ. No one's gonna like break in and arrest you. So we have some extra code here that we haven't talked about yet. This is showing how the intraclass correlation actually shows up across matrices. I'm going to skip that for right now and come back to it. So you can just focus on the parts that you know. Random intercept, empty model. Same thing in Stata, just having a random intercept to get the intraclass correlation. So there's a whole lot of extra stuff here. This is the part that you've seen before under covariance parameter estimates. So UN11, that is my school level random intercept variance in math, the 45. The within school student level, level 1, remaining variance within schools in math is the 253. Intraclass correlation is between over between plus within, works out to be 0.15. So 15% of the variation in math is what, friends? Between or within? Not a trick question this time. Between or within?
Within schools, right? So that's small.
What's on the top?
You mean the ICC?
Yeah. 15% of the total variation is... It's between. It's between, yeah. Now, what you can also think about this, and the way I think you're going is, this is also the correlation within schools. It is the average correlation of math scores from the same school is 0.15. 15% of the total variation is between schools. This is actually kind of high for clustered data. So 15.15, the ICC, is an effect size for constant school dependency, dependency in the mean. The significance test that goes along with it is right here. So it's comparing our model with a level 2 random intercept variance and a level 1 residual variance to a model that only has level 1 residual variance. Our model fits better. We'll talk more about these things here in the next unit as well. And here's our intercept. So 47, that is the mean of the school means. It's not just the grand mean, because it's not using the pooled data. It's the mean of the means. If we use the intraclass correlation and the average number of students per school of 275, I can approximate the design effect for these data as about 42. And the first time I calculated that, I was like, oh, that there's no way that can be right. And I checked and checked and checked, no, it's right. So because there are so many students within a school on average, and because the schools have so much variance across them, 15%, the 13,000 students we actually have divided by my design effect of 42. This should be 41.8. This is left over from an earlier version where I used ML instead, is 312. So in terms of effective sample size, unique students, I have 312. We can also calculate another type of descriptive statistic to describe the intercept differences. We haven't talked about this yet, but I can go ahead and show it to you because it's pretty straightforward. It's what's known as a random effect confidence interval. It is not the normal confidence interval you're used to thinking about. The normal confidence interval is about the precision of a fixed effect, like a slope or a mean. This is describing what your model says the variability across schools is in your fixed effect. So it's calculated as the fixed effect, in this case the intercept, plus or minus whatever critical region you want. So this is 95%, so we use a critical value of 1.96, times the square root of the random intercept variance. Okay, so let's think about that. What's the square root of variance? Standard deviation, right? So 95% of a normal distribution are supposed to be plus or minus 2 standard deviations. That's what we're trying to figure out here. Like, what's the window around the fixed intercept that my random intercept variance implies? So on average, school mean math is like 48, but an intraclass correlation of 0.15 means that 95% of the schools in my sample would expect to have their own means within this range, 34 to 60. So this is a way of putting some real numbers behind what is kind of an arbitrary, like, ICC concept. Like, this is how much the model predicts schools to vary in their means. So now, adding free and reduced lunch. So I add a new level 1 predictor here in model 2. Because I've picked up beta 1s in the level 1 model, I pick up beta 1s as an outcome in the level 2 model. For right now, we're giving it a fixed effect only, meaning that all schools are going to have the same student level free and reduced lunch effect. I pop that variable into the model as a predictor. It's binary, so you don't need to treat it as a class variable or a factor variable. So I'm using C dot here in stata rather than I dot. And here we go. So my new intercept, it was 47 and some change, now it's 50. So this is the expected math for a student who does not get free lunch. What happens to you if you do get free lunch? Math is lower by 9 points. A range of a variable from 0 to 83. It's a 9-point difference between students who get free lunch and students who don't. So don't get free lunch. It's bad for you. Clearly, it lowers your test scores. So I have this new scientific finding that free lunch is bad for you. Do I write this up and turn it in? No. Well, we're only on like page 2 of this handout, so that gives you a clue. But what have I just done? Which cell am I? Yeah, I just did this. I smushed it. The proportion of students who get free lunch ranges from 0 to 80%, or percentage of students, 0 to 80. That is a smushed effect. Said differently, I am assuming no contextual effect. I am assuming that after controlling for whether or not I get free lunch, it doesn't matter how many poor kids go to my school. You think that's true? Probably not, but it's an empirical question. So how do you know that this is a smushed effect other than the fact that I just told you? When you read papers, for instance, anytime you see a table of results in which you have a level 1 predictor in the table that does not appear to have a level 2 version of it in the same table, it's probably smushed. Unless this predictor has been group mean centered or naturally does not have any level 2 variation. The latter is very rare. It's smushed. But let's say that they just reported this coefficient in the text and they didn't give you a table. Here's the other way that you can tell this effect is smushed. Look at what happened to my variance components. So free and reduced lunch is a student level variable. Which of the two variances should it have reduced? Level 2 or level 1? Students are level 1, schools are level 2. Free lunch is a student predictor, so which variance should it have reduced?
Shouldn't have?
Should have.
And it should be at student level 1.
Student level 1. Is that, which row is that? Yeah, it's this one, residual. So in the empty model, my residual variance at level 1 was 253. Now it's down to 239. 253 minus 239 divided by 253 gives me this number right here. So a 5% reduction. But look at what happened at level 2. A 40% reduction in the level 2 random intercept variance. How can a student thing explain why some schools are better than others? It can't. It is the school level variance in the student thing that explains why some schools are better than others. It is the student level variance in free and reduced lunch that explains why school mean math variance has been captured. It's the smushed effect doing the work. What does this model say the smushed effect is? Right here. This 9 points. This model says that is the difference between students who do and do not get free lunch. That is also the difference in school mean math between schools that have 0 students with free lunch and 100% students with free lunch. That's what a unit is. That's what the model says. It has to be both. And note that in this handout, I did a lot of the writing for you, because this stuff is hard enough as it is without having to scribble down words, right? Yeah. So let's fix it. So I'm here. I need to go over here. I'm going to unsmush my level 1 predictor by estimating its unique effect controlling for the school mean free and reduced lunch, which is the best version of that I have in this data set that's available to me. I don't have a better version, so that's what I'm going to do. So in the level 2 model, I have a new fixed effect in the equation for the intercept, gamma 01, because this is the first predictor of beta 0. School mean free and reduced lunch minus 0.3. So my reference point is a school in which 30% of the kids get free lunch. Things that I am asking for, 2 things here that you might want to know at this point. Number 1, what is the overall effect of lunch, putting them together? The same as the test of the model R-square in this case, because there's only 2 predictors. So I have a contrast, doing a multivariate wald test for 2 degrees of freedom. What is the overall effect of lunch? And the other thing is asking for a linear combination of the fixed effects, where this is the within effect is a 1, the between effect is a 1, so this is adding them together. So excuse me, this is the contextual effect. So these added together become the between effect, which is what I would have gotten had I group mean centered the level 1 predictor. The fact that they're being added together is more explicit in the corresponding lincom and stata. I'm also saving the model predicted outcomes to a data set. In SAS, saving them as a column called pred lunch and stata, and correlating them with the real outcomes. That's going to give me total R-square. So that's a complementary effect size to talk about sort of the overall variation in math that this set of level-specific variables explains. Okay. So let me look at the coefficient from before. 9.4, minus 9.4. Hang on to that in your head. What is it now? About the same. 9.2. Now, why is that? Because 13,000 students are contributing to this point. There's only 94 schools. So the smushed effect, that's a blended effect, is weighted by the information available at each level. It's going to be pushed to be way closer to the level 1 effect than level 2. So by unsmushing it, my minus 9.4 became minus 9.2. So now, this minus 9.2 is the difference within a school, holding schools constant between a student who gets free lunch and that who doesn't. Now this one, the 16, this is the tricky one. This is my level 2 contextual effect. This is the effect of going to a school that has more poor kids after controlling for whether or not you are poor. Incremental school effect. 16 seems like a huge coefficient, doesn't it? But keep in mind what the scale is here. Fixed slopes are always per unit change in x, right? What does that mean for this variable that is a proportion ranging from 0 to 1? Per unit change is the difference between schools that have no free lunch kids and 100% free lunch kids. So that's why it's so big. It's 16 because it spans the entire range of possibility of this variable. So what might make more sense is to move the decimal place over and think about it as per 10%. And so the words that I have down here did that. So I'll move this one over to fall inside. So yes, at the student level, the difference between students from the same school who do and do not get free lunch is 9 points. Students who get free lunch score significantly lower. After controlling for whether you get free lunch, for every 10% more poor kids in your school, your whole school's math score goes down by 1.7. It's per 10% if you move the decimal. If I take, there, put this back before I forget. If I take this minus 9 and add to it the minus 16, that gets me my between school effect of minus 26. So without controlling for individual free lunch status, for every 10% more poor kids, your school's math goes down by 2.6. After you control for individual free lunch status, the school effect is reduced to 1.7. Said differently, the within effect is minus 9. The between effect is minus 26. The difference between them is the contextual effect of minus 16. Minus 16 is the test of whether or not we should have smushed. And the answer is no, because the level 1 effect is minus 9 and the level 2 effect is minus 26, and those are decidedly not the same. So the previous smushed model forced the level 2 effect that was supposed to be minus 26 to be the minus 9. So what do you think is going to happen when that level 2 effect gets to be what it really wanted to be? What's going to happen to the level 2 variance in math after the level 2 effect has been corrected? It's going to go down. because the coefficient to explain the effect of lunch was forced to be smaller than it should have been in the previous model. The coefficient of -9 explained 40% of the level 2 random intercept variance. Now the coefficient is 26. That's what it wants to be in the data. And here's what happens. By adding school mean free and reduced lunch, of the variance that remained, we got another 49% of it at level 2. So if we look at the net reduction relative to the empty model from both effects of lunch, that's this one right here, which is, I think, is a little more useful. So the fact that some schools have more poor kids accounted for 70% of the mean differences in school mean math. 70%, 69%. Have you ever seen an R-square that big in your life in real data? Not me. Now, before I go nominate myself for some prestigious prize, what should I keep in mind? What is this number out of? The ICC. What I have is 69% of the 15% that was due to schools. Still big, but not quite as impressive. Likewise, the level 1 effect, the difference between kids who do and do not get free lunch is responsible for 5% of the level 1 kid level within school math variance. So this is 5% of the 85%, the opposite of the ICC. And I've got the exact numbers right here for you. So I have 69% of the 15% and 5% of the 85%. To try and put those back together again, like how important is lunch sort of across both? Total R-square can help me answer that question. So I have the correlation between the math outcomes predicted from the lunch variables with the real ones. That correlation is 0.4. If I square that correlation, that's R-square, that's 0.16. That's my total R-square. So 16% of the total variation put back together again in just math, period, is because of lunch, period. That's a general effect size. Then more specifically, pseudo R-square, of the 15% that was due to school mean differences, 70% of that is school mean differences in lunch. Of the 85% that was within school kid-to-kid variation, 5% of that is because of free and reduced lunch status at the individual level. Put it back together again is a total R-square of 0.16, and that is different than 0 as given by the multivariate Wald test for the two fixed effects combined. Ta-da! So the way that I would think about this is that the between effect is what got the 70% at level 2. The within effect is what got the 5% at level 1. The contextual effect gives you the difference between the two as the unit of its analysis. Questions on that? Okay. So foreshadowing what we're going to do next week. Let's go back up to my equation here. My level 2 model has two terms in it. My intercept. So gamma 0, 0 is my expected math score for kids who pay for lunch and kids who go to a school where there's 30% of the students who don't pay for lunch, get free lunch, right? Then we have the effect of proportion of students in your school who gets free lunch, and then U0 is what? Random intercept. What does it mean conceptually here? U's are always deviations, right? In an empty model, if school lunch weren't here, let's go back to that. What does U0 mean here in the empty model? It's the idea that we have school level variance, but for any one school, this is how far off your school's mean is from the mean of the means, right? So if you have a school that's higher in math relatively to the other schools, U is positive. If your school is bad, U is negative, right? But this, at this point, is all the variability there is to be had across schools and their math scores. We go through and put a predictor in. U0 is no longer all the variability there is to be had. This is what's left. It's the remaining deviation between your school's intercept and the one that is predicted based on your school lunch status. So if two schools have the same proportion of free lunch kids, yet their math scores still differ, why is that? That's what U0 is conceptually. Now what about beta 1? It only has one term. This term, gamma 1O, this is the fixed effect. This is the difference for every school between kids who get free lunch and those who don't. Do you think it's reasonable to expect that every school has the exact same effect? No. So what we can do, and what we'll do next week, is add what's known as a random slope to this. We will add U1. So the starting point for this is the same idea as in the empty model for the intercept. Gamma 1O becomes the average slope across the school slopes. U1 is going to be how far off your school slope is from the average slope. Being poor might matter more in some schools than others. If so, we need U1 in the model. If so, we can start putting predictors in to explain why it is that being poor matters more in some schools. What we're actually going to do is put in this variable right here. So I would call that an intra-variable interaction between the two halves of that. Is being poor more bad in poorer schools? Or is being poor more bad in richer schools? That's my question. So interaction of the two to potentially explain this variance. But that's next week. All right. So any questions before we adjourn?
Binary variables can also be used as both beta 1 and beta 2.
Mm-hmm.
Meanwhile, in order to make sure you give contextual effect, not to observe the R-squared change. If there is a significant change, we might have the contextual effect. Otherwise, we probably should not think about it at all.
So the contextual effect is directly observable in this model as the level 2 fixed effect. So if this contextual effect is significant, that tells you that the between and within effects differ and that they need to be separate parameters. I would argue that even if it's not significant, it stays because it makes the interpretation more clear and because those parameters can change after they become conditioned on other variables. So if we add other predictors to the model, what is a relative effect at level 2 versus level 1? They may compete differently, and so the contextual effect can change as the model goes along. To me, you always keep it, because it's used to define the inference for level 1 from level 2. Yeah. But how you know that smushing happened in the real world is whenever you see a level 1 predictor that does not have a level 2 counterpart, and it hasn't been group mean centered. Something's wrong then. And that will explain, that will be the only way that a level 1 predictor can explain level 2 variance. Doesn't happen. It's the level 2 part of the level 1 predictor that explains the level 2 variance. And other terms besides smushed, I'm trying to make it a thing, so you are allowed to use that. But if it makes you uncomfortable, conflated effect, convergence effect. I like conflated because that's the same sort of idea, smushing of the two. So, broken, though. You can hang on to that one. Broken model. All right. No class Thursday because I am going to be gone. I will let you know when your next quiz is ready. Please get that done before the beginning of class next week. And you have 2 weeks to work on your homework. You can do about 2/3 of it right now. Or you can put it off until next week, your choice. So, all right. Then I shall see you all next week. Have a good one.